Have you ever really stopped to think about what's happening under the hood when you, say, save a file or launch an app? It feels instant, right? But what's really going on is this invisible, super high-stakes negotiation inside your computer. Today, we're going to pull back that curtain and meet the most important player in that whole process. And it all kicks off with one simple question.
Why can't your word processor just go and talk directly to your hard drive when you click save? You'd think that'd be way more efficient, wouldn't you? But nope. There's a very, very good reason for keeping them separated.
And that reason is that your computer is basically split into two different worlds. First, you've got user mode. That's where all your apps live, your browser, your games, everything you interact with. It's kind of like the general admission area. Access is restricted. Then you have the VIP lounge, kernel mode. This is where the absolute core of the operating system lives, and it has total, privileged, direct access to all the hardware. And this divide, it's not a bug, it's a feature. It's what stops one buggy app from taking down your entire system.
So if your app is stuck in user mode and it needs to get something done by the hardware, what's it supposed to do? It can't go there itself. Well, it needs a go-between. It needs a secure, trusted middleman who's got an all-access pass to operate in both of these worlds.
And that brings us to the star of the show today, the kernel. The kernel is that middleman. It's the absolute heart of your operating system. Its whole job is to manage all the computer's resources. We're talking CPU time, memory, your storage, and to provide that secure bridge for apps to get what they need. And the way it does that? Through a set of functions we call kernel services.
Now, an app can't just, casually tap the kernel on the shoulder and ask for a favor. Because this whole process involves crossing that super important boundary from user mode to kernel mode. It has to be done through a very formal, very structured, and totally secure process.
And that formal request has a name. And it's really the key to this whole operation. It's called a system call. You can think of it like the official paperwork an application has to file to get the kernel's attention and ask it to perform one of its services. So let's trace the journey of a system call to see how this actually works. Let's say you're saving a file. Step 1, you hit save. Your app immediately sends a save file system call to the kernel. Step 2, this is the magic part. The computer CPU literally switches from the restricted user mode to the all-powerful kernel mode in an instant. Step 3, the kernel takes over. It checks, hey, does this app even have permission to save a file here? If the answer is yes, it performs the service. It tells the physical hard drive to write the data. And finally, step 4, once the job's done, the CPU switches right back to user mode, tells the app we're good, and your app just keeps on running. And all of this happens in the blink of an eye.
Okay, so here's the main takeaway. This fundamental process, system calls, kernel services, it's universal. Every modern operating system does this. But how the kernel is actually built to provide those services, well, that's where things get really, really interesting. And it leads to two major competing design philosophies.
So this is the big debate. On one side, you've got the monolithic kernel. Think of this as putting all your eggs in one basket. All the services, file management, networking, device drivers, the whole shebang, it's all bundled into one giant program running in that privileged kernel mode. The benefit? It's blazing fast, because all the parts can talk to each other directly. But on the other side, you have the microkernel. Here, only the absolute bare minimum services are in the kernel. Everything else runs as separate programs. The big plus here, if one service crashes, say your Wi-Fi driver, it doesn't take down the entire system. It's way more secure and stable, but it can be a little bit slower.
And this is exactly why any of this matters to you. This choice between a monolithic design and a microkernel design directly impacts your computer every single day. It affects how fast it feels, it affects how often it crashes, it even affects how vulnerable it is to malware. In fact, the deep-down fundamental design of Windows, macOS, and Linux is defined by which side of this debate they landed on.
Which leaves us with one big final question to think about. As our technology gets more and more complex and security becomes more critical than ever, which philosophy is going to win out? Are we going to lean towards the raw, unadulterated speed of a monolithic kernel? Or will the stability and security of a microkernel become the new gold standard for the operating systems of the future? Honestly, that's a story that's still being written.